The following video was taken from Ace Organic Chem Elite, full of movies, videos, flashcards, a test bank, and much, much more. Plans start at less than $20. Sign up today and get 2 free ebooks with your subscription. Cancel anytime, money back guarantee if not completely satisfied, and you keep the ebooks. Just click on the link in the video notes. And now, on to our video. In this video, we're going to talk about the Diels-Alder reaction. Now, to start, I'd like to tell you that the Diels-Alder reaction is pretty important, and it is a 4+2 cycloaddition. So that's how you're going to see it written as a 4+2. Here's our 4. It's called a diene, and it's because it has 2 double bonds, diene, and then of course it will react with a diene O-file. There we are. Something that loves dienes. So a diene, 2 double bonds, and a dienophile, something that wants the double bond. You need heat. That's an important element of this. Sometimes there's a Lewis acid catalyst that'll help, but sometimes not. So heat is generally the catalyst. The reaction arrows are drawn like this, just like that. So it's cyclic. We're forming a cyclohexene, usually is our product. Not always, because there's variations of this. The key to this here is the new bond that is being formed between those 2 places. Right there and right there. So, let me try that. There we are. So those are the new sigma bonds that we're forming. And this is the driving force behind the reaction, is that we're converting 2 pi bonds. So we have 3 pi bonds. We're converting 2 of those pi bonds into 2 new sigma bonds, and we're keeping 1 of the pi bonds. This is the driving force behind this reaction. Now, the other important part is that your diene has to have electrons, because the dienophile wants electrons. If the reaction is going to work properly, unless it's an inverse Diels-Alder, then it's different. But your diene has to be electron rich. Your dienophile has to be electron either withdrawing or electron poor, however you want to say it. So I'm going to shrink this down a little bit here, and we're going to look at some examples of dienes and dienophiles. And there it goes. We're just going to put that right at the top there so you can see it, because we need a little bit of room now. What are some different dienes that we could use, and what requirements do we have on dienes? So let's start with pretty good diene, like cyclopentyl diene, right there. There's our diene. It's in there. This is locked in as it is because it's a ring. It's not going anywhere. So that is a pretty good diene. Another diene that you're going to see a lot. Right, just that simple. And that this is generally used in generic Diels-Alder reactions. You can go for cyclohexadiene. That's fine. You'll see that in a lot of reactions. Dienes that are not cyclic can be substituted, but as I'll show in a second, you need to be careful about that substitution. Here's another one that's a favorite of mine. Well, I'll get to my ultimate favorite diene in a second. But as you can see here, all of these dienes, they're pretty much alkyl, or let's say you had this. Oops, let me redraw that. There we are. You can have ethers there. Those ethers are electron donating. They're not going to react, because ethers are generally dead substituents, but that'll push electron density in and make this a better diene. Here is my favorite diene, actually. This is called Danishevsky's diene. This allows you, so TMS is trimethylsilane, that's a protecting group. So you have a silyl ether here, and you can remove that TMS to show an alcohol later. This is just a great diene for doing actual organic chemistry. Now, I promised you that we were going to see some dienes that don't work. Here's one of them. So this is a diene, right? There's our two double bonds, but this doesn't work because the dienes are trans to each other across this single bond here, and it's locked in because they're rings. This is called the S-trans because it's trans across this sigma bond. Notice every one of these here, the double bond, the diene is on the same side of this single bond right here. See, single bond right there, single bond there. These are all S-cis. And for your Diels-Alder reaction to work, your diene needs to maintain an S-cis configuration. If it can't get into the S-cis configuration, it's not going to react. Also, if it doesn't spend a lot of time in the S-cis configuration, then the reaction is going to be slower. So for example, there are, let me draw one here real quickly. There are atoms or molecules which, because of their configuration, aren't going to spend a lot of time in the S-cis configuration. Let me draw one here real quick. So this is also a diene, but because and we can have free rotation about this single bond, but if we rotate this, what's going to happen is these two isopropyl groups are going to be banging into each other. So I guess let me show the other configuration. So this is the S-trans configuration. The same molecule. I'm running out of room quickly here. I apologize. Same molecule can undergo an S-cis configuration. So that's what it has to get to react in a Diels-Alder reaction. But look, those two isopropyl groups are going to be banging into each other. So the S-trans configuration is much preferred to the S-cis because of steric considerations. So that makes this a pretty bad diene. So that is a trick that your professors are going to throw at you, this S-trans thing, and say, well, can you do a Diels-Alder reaction with this? And the answer is no, you cannot. So be wary of that. So I'm even going to write in here, just so you don't forget, S-trans is bad. So we know that there's two things that our diene has to do. It has to be electron donating, and it has to adopt an S-cis configuration. Get both of those and you've probably got a good diene. And we'll even get rid of our S-trans there for a second. Now, what about the dienophiles? Well, we've already talked about the fact that dienophiles need to be electron withdrawing. Well, what are some good electron withdrawing groups? Well, we know that ketones are pretty good electron withdrawing groups. So you will see alpha beta unsaturated ketones and aldehydes a lot as dienophiles. And those two guys can just get together, do our 4+2 cycloaddition, and form a new product. That's easy. What else? Well, you could have, what about a nitrile there? Those are really electron withdrawing. That's a pretty good one. Now you can get a little funky from here. So another one you're going to see pretty frequently is this thing where you have ethers on both ends. This is still a dienophile. That's still, it's the ethers, or I'm sorry, the esters are sucking off electron density, making this an electron poor double bond. So that's a really good dienophile. And of course, if you can have, you can also have the trans version of that. So there's a cis version and a trans version, and that doesn't matter with our dienophiles. Right, so you can have the trans version of that, and it's just going to give you a different product. And then last, one of the dienophiles you'll probably see pretty frequently is alkynes. And again, I've put esters on the ends there just to show the electron withdrawing nature of that. So there's dienes, there's dienophiles. Electron withdrawing is the key on your dienophiles. So let's take a look at a couple of examples here. Oh, one last thing before I forget. You would think that this would be a pretty good dienophile. Right, that customer right there. That is a ketene. So it's a double bond on a double bond. And there's a carbon in the middle right there. You would think that that would be a pretty good dienophile. It is not. And the reason it is not is because it will not undergo a 4+2 cycloaddition. It'll go a 2+2 cycloaddition to form cyclobutenes, and that's bad. So you don't want ketene in there. Again, that's another place your professors will try to trip you up. So let's look at a couple of examples of Diels-Alder reactions and see how they look. So in this example, very simple. We have, what's this? 1,3-butadiene. And then we have our alpha-beta unsaturated aldehyde. Oops. There we are. That's how the arrows go. We form our new bonds. And what we end up with is pretty simple. And there it is. There's not much to that. Now, one of the things I have not done is shown stereochemistry at this bond. We're going to do another video where we talk about regiochemistry and stereochemical issues with the Diels-Alder reaction. We're just introducing the Diels-Alder reaction right now in this video. This is racemic. We didn't start with any chirality here. We're not going to finish with any chirality. So this product is going to be racemic at that bond. You don't start with chirality, you can't finish with it. Keep that in mind. So let's do another example here. And in this example, we're going to get a bridging product out. So if we took cyclohexadiene right here and we subjected it to a diene, right, so this ester here, nice and electron withdrawing. We do our arrow moving, so let's move some electrons to there to form the internal, or really the only, in this case, pi bond we're going to retain. There it is. This part here, so our connection, and I'm going to show the connection. So the connection goes from there to there, which means that these 1, 2, well, I guess 1 and 2, that's going to be a bridge now. Those get kind of pushed up, and they're not part of the cyclohexene ring we're forming. That's going to be part of the bridge. And what it looks like is this. So 2 things I want you to take away from this. If we call this carbon 4 and carbon 5 right there, that's carbon 4 and carbon 5 right there. So that's our new bridge. Second, because our ester was cis, the 2 ester moieties are going to be cis to each other in the product also, and that has to do with the way it gets pushed once you form the new molecule. And we'll show how these 2 things approach each other in just a second from an orbital point of view. But take away from this that the Diels-Alder reaction can form bicyclic compounds. And if you need to form a bicyclic compound in this class, trust me, this is how you did it. Last example here, we are going to take this and let's put a methyl group on the back end right there. And we're going to subject it to, this time, an alkene. I'm sorry, an alkyne. So here's the alkyne we're going to use. What happens here? How does this work? Well, it's the same thing. And this is what I really like doing with these reactions, is you always push your arrows so you see what's going on. And if you want to, and I like doing this, I mean, make the dashed lines. Make these dashed lines so you know what you're forming. It's getting upset at me because this isn't where you should be drawing. It's okay. So there's where we're forming our new bond. There's those little dashed things. The little dashed lines show where we're going to form. And what we get out of it is a 1,4 cyclohexadiene with our esters over here and the methyl group over here. So that's an introduction to the Diels-Alder reaction and how it works. As I said, 4+2 cycloaddition, with the driving force being the conversion of 2 pi bonds into 2 sigma bonds. Last thing I'm going to show you is a little bit into the orbitals. So this is a representation of the orbitals that work in a Diels-Alder reaction. So you can have, you need to have a HOMO, or highest occupied molecular orbital, interacting with a LUMO, which is a lowest unoccupied molecular orbital. And as it says here, the overlap of the orbitals have the same color, which means they're in phase with each other. And that's how these things have to interact. Personally, I hate orbitals. I think they are so irrelevant in organic chemistry, it's not funny. But you need to know they exist, and your professors want you to, hopefully they won't have you drawing orbitals and showing what the highest unoccupied and the lowest occupied is. That could be a whole lecture, is orbitals. Just for this, I'm going to leave it at HOMOs and LUMOs need to interact. And as you can see here, your dienophile is coming in below, or it could theoretically come in from above at the HOMO or LUMO of your diene. So that's all I'm going to say about orbitals. I hope I didn't confuse you more than I helped you. Just know that a HOMO and a LUMO need to interact in Diels-Alder, and for most classes you'll be fine. Next video is going to be on the regioselectivity and the stereoselectivity that goes along with the Diels-Alder reaction.